A few weeks ago, I bought these huge capacitors. They are 6 millifarad and 350 volt DC. So I decided to make an online UPS by using them, because the lifespan of most batteries are less than 3000 cycles. But on the other hand, the lifespan of this capacitor, according to this datasheet, is 1 million times of charge and discharge. So we have a huge difference between the battery and capacitor in terms of lifespan. To make a UPS using capacitors, first of all we have to charge them up from the mains voltage. So we need a bridge rectifier to convert AC voltage to DC voltage. But when I connect this circuit to the mains voltage, the circuit breaker trip. That's because any big capacitor, when it charges up, draw very high current at the beginning for a few seconds. To solve this problem, we have to connect a high power resistor in series with the capacitor, so the resistor limiting the inrush current. But then after a few seconds, we have to bypass the resistor using this relay, because the capacitors get charged and there is no more inrush current. The delay time depends on the value of this resistor and this capacitor. So now we got 310 volt on the capacitors, which is the peak value of the mains voltage minus voltage drop across the bridge rectifier. I connect this high DC voltage to 4 MOSFETs. By switching 2 MOSFETs each time, the output voltage will be AC again. This SPWM module switching on and off the MOSFETs periodically. Then we have a low-pass filter to convert SPWM to pure sine wave. We also have a temperature sensor to run in the cooling fan when the MOSFETs get hot. This part is a voltage feedback. It keeps the output voltage stable, regardless of the load is connected or not. I convert this circuit to PCB and order it as always from PCBWay.com. It takes about 2 weeks. Now it's time to solder in the components. I'm using this MOSFET 25N50. It can handle 25 amps and 500 volt. I mount them on the heatsink with a cooling fan on the backside. You have to use isolation pad between the MOSFET and the heatsink. Otherwise, the drain of all MOSFETs short out together. I bought a display with the SPWM module, so it can read in the voltage, current, frequency, and temperature. I hooked up each capacitor to the PCB using 2 screws. Be careful with the polarity. It's so dangerous to touch the capacitor contacts when it gets charged. So I print some isolation caps using my 3D printer. The magnet inside make it stuck to the contacts. However, it's better to use an enclosure for the whole circuit. But my 3D printer cannot print big parts. Since the capacitors are too heavy, I think the PCB start to bending. So I put another PCB on the other side. Then tighten the nuts. The PCB already has some holes here. I just make them bigger using my drill. Adding a swivel caster could be useful. So now we're done. It's time to test. I connect the input to the mains voltage. The capacitors start to charge up, and after about 5 seconds the relay bypassed the high power resistor. As you can see here, the voltage across the capacitor is 309 volt DC. I'm using a 9 watt LED bulb as a load. So let's see how long it takes to discharge the capacitors. As you can see here, it takes only 30 seconds, which is hopeless. But the interesting thing here that we still have some high voltage across the capacitors. So why the load stopped working? Because this SPWM module has a feature called under voltage protection. To solve this problem, I used a simple trick. I removed the feedback circuit, then I used the resistive voltage divider here. So I connect the voltage sensing pin of the module to the voltage divider instead of connected to the output. And this voltage divider takes the input voltage from the 12 volt power supply, which is constant, instead of take it from the output. After doing this trick, the running time of the load increases to few minutes, and the capacitors discharge to about 20 volts. However, I don't recommend you to do that because some appliances can damage with very low voltage. UPS with backup time of 2 minutes are useless. But on the other hand, you can use it in many different situations. Let's say, for example, you have 2 gasoline generators and you want to connect them together to increase the output power. In this case, you can never hook up them together in parallel because there is a phase shift between the two output waveform. For example, at this moment, the voltage of the first generator is higher than the second one. So the current, instead of going to the load, it starts to go into the second generator. That means the second generator loading the first one. At this moment, however, the first generator loading the second one. So they can damage each other. This is why you cannot connect two generators without synchronization. To solve this problem, we can convert the output voltage of them to DC using a bridge rectifier. Now we can hook up them together in parallel and convert them to AC once again using my circuit. To balance in the load between the two generators, you have to set the voltage of them equal to each other by turning the potentiometer of the AVR on your generator. I used a very small load here just for this presentation. This UPS called online because there is no transfer time to switch between the grid voltage and the storage, unlike my expensive solar UPS which takes 18 milliseconds. This is mentioned in the datasheet. This one here takes 7 milliseconds. This transfer delay sometimes can restart your computer, so the second usage of my circuit, you can connect it to the output of an offline UPS. So we got online UPS, the square wave converted to pure sine wave, and the backup time become few hours depends on the battery. You can also use it to convert the high DC voltage of solar panels to AC voltage with pure sine wave. I measured the efficiency and it was 95%, which is excellent. I add a JFET here to deactivate the relay when the power cut off, and also some protection and LED indicator. I recommend you to increase the dead time by short out jumper 3 and jumper 4. Especially if you want to use IGBT instead of MOSFETs. Adding a few small capacitors here can remove any high voltage spikes. You can adjust the output voltage by using this potentiometer. The maximum output power not only depends on your MOSFETs, but also depends on this current shunt resistor. According to the datasheet, when the voltage across this resistor become more than 0.5 volt, the module detect overcurrent. So that means 5 amps, which is around 1 kilowatt. But you can increase the output current to 10 amps by using a 0.05 ohm resistor. In that case, the output power could be 2.2 kilowatts. Please like this video and subscribe to my channel. Thanks for watching.